Hello, in the last videos we discussed what is union find and some examples. Let's discuss the next question. I will attach the link in the description below, read it and give it a try. Alex has a grid with n rows and m columns consisting of dot and hash. A set of hash forms a connected component. It is possible to reach any other cell in the set by only moving to other that share a common site. The size is the number of cells in the set. In one operation, Alex wants to select a row or any column and set all the elements on that row or column to hash. Find the maximum possible largest component hash cells that can be achieved after performing operation at most once. And the constraints are the total number of cells n into m is up to 106. So what the question is saying, let's say this is the given grid and it consists of 3 rows and 5 columns. We can take any row or any column and replace all the cells in that row or column with hash, and after replacing we have to find the maximum size of largest connected component with hashes. Let's say we are trying to replace the 0th row, so after replacing all by hashes, the maximum size will be these 5 and 1 6, because these two cannot share a component because they must be shared by side, not diagonally. And let's say we are trying to replace the first row, then what is the answer? Then 5 plus 4, it will be 9. And let's say we are trying to replace first column, second column, 0 1 2, and then what will be the answer? It will be 3 plus 3 plus 1, it will be 7. So in this way, if we try to do all the possible options, and finally the answer is 9, which is maximum possible, so return 9. So let's say first we try to find the answer for rows, then we can try to use same method for columns as well. And now let's assume that we are trying to find the optimal answer for rows, and let's say we are at some second row of the new matrix. So this is the new cell, new matrix, new grid, and let's say we are at this row, second row. How can we find answer? We are starting from the first column and we are at this column. And standing at this column, what is the answer that we want to add? We want the largest component size, right? So we want the sizes of components from above and below. If they are hashes, for example, we are at this point and this is hash. So obviously we are trying to replace everyone with hash. So we are replacing this by hash. So if above is hash or below is hash, then we are getting more number of hashes, because if this is dot and above is dot and below is dot as well, even if we are trying to replace this by hash, there is no change in answer because we are only able to increment one but not by above or below cells. So we are standing at dot, and if above is hash or below is hash, we want the size of the values so that we can, because we are replacing it, so the answers for above cells also will be incremented now. And similarly for all, for example, we are at this and we want the size of component above, and this is hash, so we are replacing this by hash, so this will lead to addition in answer. And what is the answer that gonna contribute by this? It will be the number of components that is attached to. So let's start BFS from this and let's do BFS. So we will reach this and we will reach this because all are hashes, so we can reach all the values. So we will reach this and we will reach this as well, and all the other are dots, so we will stop. And what is the size? So it will be 5, and answer plus is equal to 5. And now we reach this, it is 0, and it is above, it is 0, it is dot, so no answer possible with respect to this. And coming to below, it is 1, so we will do BFS, and this is the only cell, so it is 1, so it will be 1. And similarly, let's say we are at this point and above is hash, and it is already visited by some above 1, so no need to consider because it is already contributed in the answer, and it is hash, it is at, so and so on. Let's continue. So in this way, what is the time complexity? So for every column we have to run BFS, so it will be at least nm, and it will be at least nm for BFS as well, so for every BFS. So obviously this is not possible because nm is up to 106 and nm whole square is not possible. So now what is the main goal? The main goal is to, we want the size of connected components of above and below rows if it is a hash. So let's say we found some method that gives sizes of connected components of 1. So let's say this is the original grid, and we found some method which gives sizes of some value, size of I of j will give the size of component starting from ij. So what will be the new sizes of vector matrix? It will be these all are 5, this is 1, and these all are connected components, so these all will be 3, and this will be 5. And now let's say we are going with this row again, and we are at this 0, and we are looking above and finding and checking whether it is hash or not. So if it is hash, add with the size. So it is hash, so yes, add with size. And now coming to this 0, above is dot, so 0, and below is hash, and what is size corresponding to it, it will be 1. And again let's come to next one. So above is 5, so add 5, below is 0, and so on. But if we clearly observe one thing, we are adding 5 two times, right? Because let's say we try to think of a set, because duplicate elements are possible. If we are trying to use set, what if we have two connected components of same size? Let's say this is 5 and these two are also 3. These two are also hashes. So all of these will be 5. So these two also will be 5. So if we try to replace sizes in set, the answer will be reduced, because we discussed that if you have two connected components of same size, the answer will be counted only once. So obviously we cannot use it, and obviously this method is not correct. So how can we optimize this, or how can we find correctly? We are counting size of same component of multiple times. So we want unique values of component and insert all in set. So we discussed that storing the sizes in set is useless, because that will not give correct answer. But what if we try to store unique value of every component in set, and if we try to add sizes after inserting in the set? So that works, because so let's say this is 1, right? This is the unique component will be 0. The unique value of this component is 0. Assume that it is 0, assume that it is 1, and assume it is 0. So from the before thing, we saw that we cannot add sizes to directly set. But what if we are at this and we try to add leaders, the unique value of every component? So we are at this one, and if we try to find the above one, it is hash. So add the 0 to hash to set. It means that it is not the size, but it is the leader node of the connected component. And similarly, come to below, it is dot, so no use, it will be 0. And come to this, let's assume this is 3, and the unique component is 3, and so on. And now when we reach this again, if we see above, it is hash, so we will add 0, but it is set, so there is no use. So in this way we try to add all in the set, and after completing traversing the row, then we can add answer of size plus 0, size plus 2, and so on. So in this way, if we try to observe, we can use DSU, because we want unique value of every component, so that if we try to insert in set, then we can get the answer. So why is DSU used here? Because for finding the leader of component, and also for finding sizes in often. Because in the previous videos we saw how to use union by size. So by union by size, we are storing a size vector where size of unique value represents the total count of nodes in that connected components. So that is useful here as well. So by this both, we can see that TSU useful here. And so initially we will merge all by hashes, all by DSU. So initially we are at this, and if this is hash, then try to merge with the next ones. If those are hashes, for example, this is hash, so the next is hash, yes, so merge these both. And this is also hash, so merge all these 3. And this is dot, so don't add. This is dot, don't add. And this is hash, yes. This is hash, yes. So this is one connected component. And similarly, we'll go to this not hash, so don't do anything. This is hash, so yes, but this is dot and this is dot, so we can't do anything. And similarly, we will come to this, only this. And in this way, we can find connected components by DSU. And then we can find leaders also. So we already discussed that we will pre-compute sizes and leaders of all the components while directly merging the DSU initially. So we found that we will add the leaders into leader set, and after we will traverse the set and we will add size of that root, and we can get the answer. And finally, not only this, for example, we are adding hashes also. If initially they are hash, it is no use, but if it is initially dot, then we are replacing by hash, so obviously we will increment answer. So plus 3, why 3? Because 3 is the number of dots in the present row. So while traversing, if that is dot, we can increment the answer, and we can insert the leader of above connected component and below if they are hashes to set. And if it is hash, so simply add this one to set and continue, because originally it is hash. So by replacing with hash, we are not adding, we are just replacing. So if it is dot, add answer, else just add into set. So we discussed how to do, but In a DSU of single, for example, if this is only tree, then we can find DSU as it is 1D. But here it is 2D. So how to find the leader? Because leader in 2 dimensions is meaningless. So we can simply use some method or formula which converts ij to single value, because the unique cell can be represented by ij. So the value it can be represented in 1D is some function. So let's say this is 0, this is 1, and so on till m minus 1. Because this is n rows and m columns, so this is the last column, it will be m minus 1. And what will be the next value? It will be m. So let's assume that it is allotted to the first row 0th column, and similarly m plus 1, m plus 2, and so on till 2m minus 1. And similarly this will be 2m minus 1. So if we try to observe this, it will be simply I into m plus j, because let's say we have 1 comma 0. It means that what will be the new value? It will be m. So 1 comma 0 is m, which is correct from this. So in this way we try to assign every I comma j a unique value, so that we can get the unique leader or unique parent for a component in a scalar value, which is like 3 or 5 or something, but not in 2D. So for the last cell, which is n minus 1, m minus 1, what will be the hash value? What will be this one? It will be m into n minus 1 plus m minus 1, which will be n minus 1. So 0 to n minus 1. So these are the number of cells. So for every cell, we found a formula to reduce it to single value. So in this way, we will traverse the every cell and we find the reduced value, which is I into m plus j. So for every cell, we will find the reduced value, which is 1D, and similarly, we will try to merge all those and we find the answer. So let's check the code. We are inputting the n and m, and we are initializing parent to nm plus 1, because the size is n into m. So let's add plus 1 for edge cases and n plus 1 as well, and initialize all parents with I, and similarly initialize size with 1, because initially every node is a connected component itself and the size is 1 and the parent is itself. So initializing size with 1 and parent with I itself, and inputting the value, and and we have to merge the DSU, right? So we will traverse the every cell, and if it is hash, then try to merge with the other 4. So k is equal to 0 to 4, so we are traveling up, down, left and right. So if the new cell is valid, then merge. So then merge what? The reduced value of this one and the reduced value of that cell. Reduced value of this one, what? It will be I into m plus j, because we have discussed before. And similarly, I plus dxk is the new I, and j plus dy is the new j. So simply it will be new I into m plus j. And when it is valid, so it will be valid when it is in the boundary, and it is hash, because we can connect only if they are reachable by side and both are hashes. So if they are valid, then merge. So after this, what we are getting? So after this, we computed sizes, because in merge we will do sizes as well, because let's check the code. In the merge, we will find the parents, and if those both are equal, return. No need to merge, because they are already merged. And if size is less, we are incrementing size and adding to the parent, because we discussed in the last videos very clearly. This is called union by size, so that it can be useful to find sizes in OF1 as well. And so after this, we found the sizes and leader of every connected component as well by DSU. And now the answer is 0, and we are trying to replace every row by hashes and finding the answer. So we are traversing 0 to n, and inside this we are at ith row, and we are trying to replace all columns from 0 to m by hashes. So let's temp value is equal to 0. What is that? It is the answer possible when we are trying to replace the current row with hashes. So it will be temp is equal to 0, initially 0, and we are initializing a set which will contain the leaders connected component unique values, and we are traversing every column, and if that is hash, just insert the reduced value to the set we discussed before. If it is dot, then increase the answer, because originally it is dot and now we are making it hash, so increment the answer. And now check the up value. So what is the up value? It is I plus 1 j. So if I plus 1 is less than n, and if it is hash, then insert that reduced value to set. It is just the unique value or leader, but not the size. And similarly check below. If it is, so it is a I minus 1 j. So if it is hash, then insert the reduced value of that connected component. And after completion of the whole traversal of grid, we will traverse the set, and we will increment temp plus is equal to size of it, because it is the unique number or leader of that connected component. So size of that will be size of that value. size of counter component. So it will be simply answer price is equal to size of id, and we are trying to maximize our answer. So we'll do for every row, and similarly for every column as well. So we'll traverse every column and we'll do the exact value, exact same. So when we are at ij, we are trying to check with the next and previous columns, right? So I in ij plus 1, ij minus 1. So similarly for wave of we can do. And finally we can return the answer. In this way we can find the answer. If you have doubts, comment below. See you in the next video.